Hi, everyone. My name is Megan Dwyer. It's nice to meet you all through video. I'm one of the live streaming teachers for Fiveable, and I'm excited to get to talk to you tonight about part one of continuity. So let me just share my slides with you so you can see. Okay, feel free to talk it up in the chat or ask me a question. Let me know that you're here and that you can hear me. Can anybody hear me? Awesome. Okay, great. Great. Okay, so later I'm going to talk to you about part one of continuity. Later on this week, Mr. Kossoff, another awesome AP Calculus teacher, is going to be talking to you about part two with a little more information. But here's just something to get us started off. First, if you don't already, please follow us on Twitter, Instagram, or on YouTube at Think Fiveable to hear about whenever we're streaming. That's where all of our videos will be posted, and we'll post when our streams are coming up. Okay, so for today, we have four main topics we're going to go through. First, we've got graphs in continuity, so an intuitive sense of just kind of looking at a graph and how do we know what is continuous. Then we'll go over a formal definition of continuity and what we think of continuity as in calculus. Then we'll go through continuity in different types of functions that you probably should have learned in pre-calculus, and how we can kind of generalize functions and their continuous behaviors. And then we'll talk about piecewise functions and how they're special in continuity. All right, so first, I would like you guys to answer in the chat, what does the word continuity mean to you? Now, this doesn't necessarily mean continuity in calculus, but just when you hear continuity, what do you think? What other words do you know that remind you of this word? Doesn't stop is good. That's a good option. Keep going forever. Exactly. Okay. Kimberly just had a really great point. Drawn without picking up your pencil. That's a really great way to think about it. If you can draw the entire graph and not have to pick up your pencil at any point, you have a continuous graph. That's a great definition that does not yet involve calculus, but we have a calculus definition for it. Okay. So next, I'm going to show you three graphs, and based on those three graphs, in the definitions that we just discussed, I want you to tell me if you think the graph is continuous or not. And again, you can respond in the chat and look at others' responses. So here's our first graph. Do we think this graph is continuous? Can we draw it without picking up our pencil? Awesome. I'm seeing lots of yeses. Yes, it is continuous. Great. It's not necessarily straight, but that it doesn't have to be straight to be continuous. It just has to not have a place where it stops or have a place where we would have to pick up our pencil to move to a separate part of the graph. Awesome. Okay, we're going to look at the next graph now. What do we think? Is this continuous? Okay, good. Answers are starting to come in. I'm seeing no's. Why no? Okay, we're coming in with some calculus definitions that we're actually going to get into later. That's awesome, Samantha. So I'm hearing yes and no. There are holes in the graph. Yes, those points where the circles are not colored in, those are holes. But we do have values at those points because we have colored in circles at the same spots, at -2 and at 3. But is it continuous? So going back to Kimberly's definition, can we draw this whole graph without picking up our pencil? No, right? Yeah. So since we cannot draw this whole graph without picking up our pencil, we cannot say that it is continuous based on the information we have now. If we are looking at this entire graph, there is no way to say that this is continuous. Okay, one last graph before we move on. Is this graph continuous? Awesome. Yes, I'm seeing lots of yeses, and you are right. This graph is continuous. It does have a weird place where we are kind of at a corner. What kind of graph is that has a corner? What types of functions do you know about that this might be? Absolute value. Awesome. Great job. So this is an absolute value function, and yes, it is continuous at any point. Even though we have a point where we kind of have the graph coming up in two directions, they still meet. There's still a value at that point. We'd have no hole. So this is a continuous graph. Awesome. Okay, so now we're going to look at the calculus definition of what makes something continuous at a specific point. Okay. So this is something that you might want to write down in your notebook and remember. So now that we have an idea on continuity, we should talk about what it means in calculus. So the graph of f of x, so any graph, any function, is continuous at a point, let's call that point A, if the following three things are true. So first of all, f of a has to exist, right? We have to have a point that if we plug in an x value, we get a y value. If there's no y value, then it's definitely not continuous because we have to have at least a hole there. Next, the limit as x approaches a of f of x has to exist as well. Now, while that's what the definition says, I hope we know that in order to show that that limit exists, there's actually a couple steps within that. Does anyone know how we can show that the limit as x approaches a exists in a function? Okay, derivatives is good, but besides derivatives, let's say we don't know the derivatives yet. How do we show a limit at a point exists? What two things need to be true? Okay, awesome. Samantha and Davina, you have really good points. So yeah, the limits from either side have to be equal. So we have to make sure that the limits from the left and from the right, they both equal the same thing. If they don't equal the same thing, then the limit can't exist. Okay. So lastly, the limiting value we get, if it exists, it must be equal to that f of a value, the value we get when we plug a into our function. So really, the entirety of this definition is included in our last statement, because in order for the limit of f of x as x approaches a to be equal to f of a, we need the other two to exist. If they don't exist, we can't get to the third part. But without the third part, we do not have a continuous function. Basically, everything needs to line up, so there's only one possible point and value and limiting value as we're coming to a certain point. So do your definitions back up that point? That definition we had of the pencil not picking up the paper, does that fit into this? Okay, good. So yeah, sometimes, most of the time, if we have a hole, it might not look like we have to pick up our pencil, but we really do. We're still skipping a point. So it really does basically fit into that, but we want to make sure that on the AP exam and when we're using calculus, we are using the calculus definition to prove why something is continuous or why it is not. So what I'm going to do is I'm going to show you those three graphs again, and this time I'm going to pick specific points and ask you if it is continuous at those points. Okay, so looking at this graph, do you guys think this is continuous at x equals 0? Okay, great. I'm getting lots of yeses. So what is f of 0? We need to prove this using calculus. Does it exist, and what is it? Awesome, great. Okay, and now that we know what f of 0 is, and that f of 0 is 8, what are our limits from the left and the right as we're approaching 0? Okay, good, Megan. Thank you for specifying that from the left and right. Yeah, Kimberly, from both sides. Yes, that it's 8 from both sides. F of 0 is also 8. So we have a continuous function at this point. We could use those steps in either. And so the last step on AP, that what they tell us to do is just to say, yes, the limit equals 8. The function also equals 8 when we plug in 0. So we do have a continuity at the point x equals 0 on this graph. Okay. All right, looking at our next graph. What do you think about the graph at x equals -2? At that specific point, is this function continuous? Okay, so I see we're thinking about the closed circle. Okay, so the first question I have for you, since we have to prove this using calculus, is does f of -2 exist? And what is it? Yes, okay, great. So what is f of -2? 1, awesome. Okay, so that should answer the question of the closed circle. We do have f of -2, and that is 1. So we know that f of -2 does exist. So we have made the first part of our definition of continuous true. How about the second part? Does the limit as x approaches -2 exist? Okay, great. We've got some great explanations in here. Awesome. Okay, so I see. Sorry, just reading your explanations. They're all very good. Okay, great job. So from the left side, we see that the limit as x approaches -2 of, let's call this f of x, our function, is 1. But if we're approaching from the right, we get a limiting value of 4. Because of that, the limit does not exist. Okay, since the limits don't exist, this function is not continuous. There's no way we can draw without picking up our pencil. There's no way we can know what the limit is. So we can't even get to step 3 because step 2 isn't true. All right, what's the other point where we're going to see discontinuity? 3, good, that's going to be 3. So 3 is a little bit different because f of 3 still does exist. We have a point at 3, 3, 3 is our point, but we've also got limits from different sides that are on totally different points. So each answer you get is going to be different. If none of your answers line up, there's really no way it can be continuous. Are there points on this graph where you could say this graph is continuous? It's okay, good. At f of 0, Jonathan used an example. I like that. Awesome. So yeah, what are some examples of where this graph is continuous at certain points? F of 4, yep, f of 4 works. That's good. 2, awesome. Good. So when you're looking at questions on the AP exam, on tests that your teachers are giving you, you want to watch for what point they're asking you if it's continuous at, because that is the point you want to test and make sure. Sometimes you can be given a graph like this. If you're asked if it's continuous at a point that is continuous, you could have continuity on a graph that in general does not have continuity. All right, last graph. What do we think? Is there any point where this graph may not be continuous? Okay, so let's test out f of 4, because I see we're talking about f of 4, and that's really the point of interest here. So does f of 4 exist, and what is it? We want to know, yep, good. Okay, great. So f of 4 does exist, and it is 2. Now, what's the limit as x approaches 4 from the left of f of x? Great, and how about the limit as x approaches 4 from the right? Awesome. Okay. And does the limit exists, the limit as x approaches 4 of our function is 2. And now we just have to test, is that limiting value equal to what happens when we plug 4 into our function? Are they both 2? Yes. Awesome. Okay. So yes, this function is continuous. F of 4 might look like it would make it not continuous, but as long as those 3 rules are satisfied, this is a continuous graph. Okay, going to move on to the next slide here. So we've got different types of functions, okay, that we have learned throughout pre-calculus, and it would be a lot easier if we could figure out maybe some ways to tell if a function is continuous by looking at it or its certain characteristics. So what we're going to do now is go into Desmos. I'm going to share a different screen with you now, so hang on one second. Okay. Hi, everybody. Let's see. Okay, here we are. Okay, can everyone see the Desmos page I have up? Okay. It's small. Okay, let's see if I can make it bigger. How about now? Great. Okay. So what we're going to do is look at this function by function. So our first function here is sorry, not piecewise. What is this function? You guys tell me, because obviously I can't say it right now. What general name do we give this type of function? It has pieces that look like a parabola, but it's more general than that. Okay, awesome. Polynomial. So yeah, this function is a polynomial. What that means is it's just made up of a bunch of terms of different powers of our variable. It has no fractions. It has no radicals. It's just a terms of different powers. Okay, and this kind of looks like our first function that we looked at. Does this seem to have any discontinuities anywhere? Or does this seem to be not continuous anywhere? No, okay. Can you guys think of polynomials that you know of to any power that might show discontinuity? No, okay, so I'm still seeing a lot of no's. So awesome, that is a generalization that we actually can make, that if we have a polynomial function and you're being asked if that polynomial function is continuous, you can always say that is continuous. That is a big help on the AP exam, because you don't want to waste your time proving something is continuous when you can just say this function is continuous because it's a polynomial. Okay, so write that down in your notes. Any polynomial function is continuous. Okay, let's look at our next function. Do we recognize this? I know you can see the function, so you know it is a sine function. Awesome. It's got an amplitude of 4, so instead of going from 1 to 1, it goes from 4 to 4. Knowing sine and what we know about its oscillation, do you guys know any places where sine might have a discontinuity? Okay, awesome. Still nowhere. Yeah, so I agree with you. There is nowhere on sine in our oscillating function that goes on forever in both directions that will ever see a discontinuity or a place where the graph has a not continuous point that doesn't follow our definition. So what other trig functions can we make this assumption about? Cosine, awesome. Yeah, so cosine also follows this. It's the same oscillating function. What about our other trigonometric functions? We've got tangent, cotangent, cosine, and secant. What do all those functions have in common, those other trig functions? Okay, so I actually want to combine the two answers we just got. So we have that they are continuous too, but also that they have asymptotes. So yes, so the way we define those other trig functions, our tangent, cotangent, secant, and cosecant, is by saying that yes, they're continuous, but only on their domain. Okay, so again, let me say that for you guys, for your notes. The trig functions are continuous, but only within their domain. So if you're looking at a problem and it's asking you if a trig function is continuous and it's using points or x values that are within the trig function's domain, then yes, you are looking at saying that that function is continuous. Just got to make sure you're testing and make sure you know where those asymptotes are. Okay, this next one is going to take me a minute to, actually, no, this next one's fine. So let's look at this one. What do we have here? This is the parent function for what type of function? Inverse is one word for it. There's actually another word I'm looking for besides inverse. Reciprocal is also a word, but that's also not the word I'm looking for. But those are both really good words. What's another thing for a function that's always a fraction? What kind of a function is that? Okay, we're getting closer. It actually is rational. So this is called a rational function. Rational functions are functions that can be written as fractions. When you have a variable in your denominator, you usually get something like what's shown on the screen right now. So what does this graph have? It's good. It looks like it's got, yeah, it's got asymptotes. It's got two asymptotes here, one at x equals 0 and one at y equals 0. Okay, so what we're looking for here is that this is kind of like the same definition I gave you for the trig functions. This is continuous except at x or y being 0. Okay, so again, we're looking for making sure that we're within our domain when we are solving problems with this function. So we do have points where the function is not continuous, but there are a lot of places where you could have a piece of a continuous function. So we just have to check the point, make sure we are continuous at that point. And if not, then we can say no. If we are, then we're good. Okay, this next one's going to take me some time. I've got to click all of the rest of these open. Almost there. Okay, and let's just zoom out of this a little bit so you can see the whole thing. Okay, great. So we're looking at, what type of function is this? What would you call this? Considering that I had to click on 3 different functions, that might give you a clue. Yes, okay, good. This is a piecewise function. So we're looking at pieces of a function that we're fitting together into one function and saying that they're only true for certain parts of their domain. If not, we couldn't have a function because we'd have overlapping inputs for one out, or overlapping outputs for one input. Okay, so this function, like we saw earlier, is really not continuous, right? We've got points of discontinuity in a couple places. I see one at 0. I see one at 2. Are all piecewise functions always going to have pieces that do not connect at the ends? No. Okay, good. So I'm going to do something that will hopefully show you another way we could have a piecewise function. Let's see. So if I change, let's see, I'm going to change this to negative. Let's turn this upside down. Okay. We don't need this point anymore at 3, 5. That point, actually, where is that point now? That point is now at 3, -1. Okay, and let's take this and let's turn this into, instead of x plus 4, x plus 2. Okay, and now we've got this point that moved down to -4, -2. Okay, good. And let's move down this point from 0,4 to 0,2. Okay, good. Okay, so this is still a piecewise function. There's still different functions making up different pieces of this graph. But now, is the graph continuous at x equals 0? Okay, good. So yeah, piecewise functions, sometimes they show discontinuities, but sometimes an entire piecewise function can be actually continuous as long as the points where those functions split line up at the same point, as long as the limit from either direction is the same. So what else could I do? Is there a way I could make this entire piecewise function continuous? What could I do to the third piece of the function to make the whole thing continuous? Okay, Megan, let's try it. Move down 1. -1. Awesome. Okay, you're right. And then we don't need this point there. Yeah, great. So now we've made a piecewise function that is continuous. And so sometimes piecewise functions can be continuous on their entire domain. Sometimes they might be continuous only at points within the function or between where your x value domains switch pieces. Okay, great job with those. So now, if you give me a second, I'm going to switch back to my PowerPoint, or well, my Google Slides, not my PowerPoint. Let's see. Okay. Okay, can you see my PowerPoint again? Yes, okay, great. Awesome. Okay, so to summarize what we just learned about functions before we go into practicing it and functions and their continuities, polynomials are what in terms of continuity? What can we assume if we see a polynomial? Always continuous, yes. No matter what, if you see a polynomial, it is always continuous. When we see a trig function, a rational function, yeah, a trig function or a rational function, what are we looking for? What do we have to make sure about the points? Awesome. Okay, great. Great. What are some other functions that don't have domains that are completely negative infinity to infinity, completely all real numbers? Exponential, great. That's one. Absolute value, good. Logarithms, yep. So logarithms are only continuous when the value inside of the logarithm is positive. Quadratic actually is a polynomial. So that is a good example of one that you don't actually have to show, because you can say, since a quadratic is a polynomial, it is always continuous. But log, exponential, those definitely you have to make sure you're within the domain. Okay. All right. So we're going to move on to some practice problems soon. But before we do that, I just want to make sure we review this definition again. Okay. So when we're doing continuity from a point, that point has to have a y value. That x value has to have a corresponding y value. The limit at that same x value has to exist from the left and the right, and they have to be equal. And that limit that you get has to equal the point that you got at the beginning. So that is the definition we are always thinking of when we're talking about a continuous function in calculus. We always want to make sure those things are true. The things we want to test for, if we think that these might not be true, are looking at their domain. Are we within their domain? And looking at if it's a piecewise function and where those pieces split, is there going to be a point of discontinuity where the graphs do not line up? or do the graphs always line up? Because as we've seen, we could have either situation happen. Okay, so now we're going to move into practice problems. So these are something that you might see on the AP test, the problems I'm about to show you. We're going to start by looking at if a function is continuous on an interval. So we were just talking about domain. And so if the interval is within our domain, we're looking at a continuous function. Then we're going to talk about if it's continuous at a specific point. In both cases, we're using our definition. And then we're going to talk about how to find values that make a function continuous. So at this point, I want to remind you guys that if you want to practice, make sure you have notebooks out. Right now, we're going to treat all of these as no calculator, so you do not need a calculator. If you want to test some of these functions in your calculator, feel free. But most of these questions will be in the no calculator portion on the AP exam. Okay, so where we start, we're going to be making sure that we're continuous on an interval. All right, so I need to share a new screen with you, so give me just a minute to do that. I'm going to be writing these problems out on my iPad, and hopefully you will be able to see them. So I'll need you guys to let me know if you cannot. But let's see if we can get this screen up for you guys. Okay, let's see. Let's switch screens now. Okay, can everyone see my OneNote screen? Okay, awesome. Now, I'm somewhat new to writing on this, so I may need your patience if something doesn't come out very clear, and I need you to let me know if it does, but I'm going to do my best. So our first question we're going to ask is, oh, need the pen. On what interval is this function continuous? And we're going to call it f of x. Is f of x continuous? Okay, so here's our function. We've got a nice big piecewise function with 4 parts here, so make sure you leave some room. We've got e to the x when x is less than -2. We have x cubed plus 3x when, let's see, -2 is less than x, which is less than or equal to 0. We have 3x over x minus 1 when x is between 0 and 5. And then last but not least, we have sine of 4x when x is greater than 5, greater than or equal to 5. Okay, awesome. So we've got a function. So far, we've really been looking at this in terms of graphs, so it's nice to see it in terms of a function. We'll walk through this one mainly together. If you guys have questions, remember to do the Ask a Question tab, and let me know. I'll stop and answer it if I can. So this is actually a multiple choice question. So we have 4 options here. Option A is the interval -2 to 2. Option B is -4 to 0. C is 4 to 6. And D is 0 to 3. Okay, awesome. So the first thing I want to do is go through these functions and talk about, do we think that they're going to give us any issues in terms of their domain or the points that they meet? So we already have a piecewise function, so we're definitely going to have to check for that. But are there any functions on here that we know already we don't have to check their continuity? Which pieces of these are definitely going to be continuous everywhere? Polynomials. Okay, so our second one right here, let's see, this has a domain of all real numbers, right? So let's just put our symbol for all real numbers right next to it. good, and sine of 4x, good. So both of these have a domain of all real numbers. We're not going to find anything within those intervals that is going to make us have a point of discontinuity. All right. What about 3x over x minus 1? Is there any point where that function is not continuous? Okay, good. So what I'm getting here is that in the domain x cannot equal 1, everything else is okay. Okay, great. Awesome. So what about e to the x? Do we have a domain of all real numbers? Yeah, e to the x, we can plug in anything we want. The only issue is we might not get, we have a horizontal asymptote, so there's y values we won't get. So we can plug in any value here, all real numbers. Okay, all right, so the next thing to check, we've got these 4 points. The next thing to check is, are these, since we're in part of a piecewise function, are we continuous within each piece of the function? So we know that we've got these different pieces where the graph is going to split. So at -2, e to the x stops and x cubed plus 3x starts. From 0, that function stops, and 3x over x minus 1 stops. So what do we need to do with those points to check to see if we're going to have continuity in between those points? Okay, Megan, that's exactly right. So we want to find f of -2 in both cases. So we want to look at, oh, actually, good catch on this. This should have less than or equal to -2. Okay, so we want to see if f of -2 exists in both cases. So let's say we plug e to the -2. We get e to the 1 over e squared. Okay, I'm not going to simplify that any further for now. And then here we get -2 cubed plus 3 times -2. Now, without even completing 1 over e to the -2 and seeing what that is there a way we can tell if these functions are going to be equal at this point? Is 1 over e squared ever going to be -14? No. Okay, good. So one way we know is that 1 over e squared is never going to be negative. There's no way that can be negative, so there's no way it's ever going to be -14. One thing I want to make sure to clarify here is that f of -2 is one value. F of -2 is 1 over e squared. That's true. What we're testing here is if the limit as x approaches -2 from the left of f of x is equal to the limit as x approaches -2 from the right of f of x. And in this case, from the left side is from the e to the x side. So we get 1 over, let's put a question mark over here so we know we're testing it. We get 1 over e squared. Is that equal to -14? No, you guys already told me no. So that is a point of discontinuity. It is not continuous at that point. So based on that, is there any points we can rule out here? Any multiple choice? Okay, yes, I agree with B. So B has an interval that has the point -2 between e and x cubed, e to the x and x cubed plus 3x. So it can't really be B. because we know that -2, it is not continuous. Okay, can we rule out A though? What about A? Okay, good. A only from the left, right? So this is an open parentheses, right? So we're just saying -2 from the left, from where it starts, and from the right side is the only place we're looking. So no, A is still a possibility. Okay, so what about between our functions x cubed plus 3x and 3x over x minus 1? What point do we have to test between those two to see if they connect? What x value? Okay, 0. Okay, great. What is, well, f of 0 we know. F of 0 only has one value, and that is connected to x cubed plus 3x. So f, oh, hang on, writing off the screen a little bit. So f of 0 equals 0 cubed plus 3 times 0. So f of 0 equals 0. We have that. Now we have to test. Sorry, guys, I have to scroll up. I hope you have it written down so you can see the function still. We've got a test now the limit as x approaches 0 from the left, and see if it's equal to the limit as x approaches 0 from the right. Now, the limit, let me get this a little neater here if I can. The limit as x approaches 0 from the left means we're looking at the function where, let's look at it again, sorry, just so I can show you. We're looking at the function where 0 is the highest thing it can be. Everything that's in that function is to the left of 0. So we are using the piece of the piecewise function that is x cubed plus 3x for this. But we also have to test from the right, we're going to be using 3x over x minus 1. Okay, awesome. So if we plug it in from this side, we get 0 cubed plus 3 times 0. So we get 0. If we plug it in from this side, we get 3 times 0 over -1, which is also 0. So does 0 equal 0? Yes. So we've got the limit as x approaches 0 of f of x is 0. And we have that f of 0 is 0. So because the limit as x approaches 0 of f of x equals f of 0, it is continuous at that point 0. Continuous at 0. Great. Okay. So based on that information, I really want to say that it will definitely be continuous through A from -2 to 2. I really think that's the right answer, but I want to make sure I'm checking these other values. So if I'm looking at option D, which is 0, 3, that is within my 3x over x minus 1, my entire interval. I'm sorry, what is A again? A is -2, 2. So, yep, no problem. So what I want to look at now is we've ruled out B. We think it could be -2, 2. That's a good possibility. It looks continuous because we know our polynomial is continuous, and we know that our function, let's see. Actually, I'm sorry. I think this should be -2, 1. My bad. Okay, that still should be continuous. So we're going between -2, which starts on x cubed plus 3x, and we're going to our next function, 3x over x minus 1. Awesome. Okay, so looking at option D, which is 0, 3, we've got a function here, 3x over x minus 1, which is, that whole interval is within that. 0 to 3 is within 0 to 5. So shouldn't we automatically think that that could be a possibility? What's wrong with that possibility based on what we've already found in the domain? Okay, Corey, great. Yep. Okay, so within this interval at D, we've got 1 within that interval. Awesome. So we can't say that D works because D has a point value inside that is discontinuous. So no, it is not continuous on 0 to 3. All right, so we ruled out D. What about C, option C, 4 to 6? That is between 3x over x minus 1 and sine of 4x. What do we think about that option? Do you guys have any strategies for checking to see if that is right? Okay, so I see C is correct, but what we have to check is there is this that is in between the interval, and it's in between the interval. Yes, good, exactly. So we want to check to see if it's continuous at 5, because if it's not, then we can't use option C. Okay, so scrolling down again, we've got our functions. I'm just going to write the pieces of the function we're focused on. 3x over x minus 1, not a limit, x minus 1 from 0 to 5. Not including 0 here. There we go. Okay. And then we've got also sine of 4x from x is greater than 5. Okay. So going through our limit definition, we want to first know f of 5. In order to find out f of 5, we only have to plug it into the function where it's equal to 5. So we just have to plug it in here. 3 times 5 over 5 minus 1. We get 3 times 5 is 15 over 4. That is our f of 5. So it exists. We've got f of 5. Now we have to test our limits. So the limit as x approaches 5 from the left is going to be from 3x over x minus 1. Okay, and the limit as x approaches 5 from the right is going to be coming from sine of 4x. Okay, so if we plug in our limit here, we're going to get 3 times 5 over 5 minus 1 again, which again becomes 15 over 4. If we plug in here, we get sine of 4 times 5. Sine of 4 times 5 is sine of 20. Okay. Do we know if those are equal or not? Now remember, this is no calculator. So yes, you could plug them into your calculator and see that they're not equal. But is there any other way we know, based on what we know about these functions, that we could tell that they're not equal? Okay, so ways we can look and see if they're not equal. Oh, okay, check to see if it is continuous at 5. Sine of 90 is 1. Okay, so sine of 90 is 1, but that's 90 degrees. Right now, we're talking about 20. And in calculus, whenever you plug a function into, or a number into a trig function, you're always talking about radians. So that's something to make sure of when you are taking the AP test. Your calculator should be in radians all the time. There's no point where calculus is ever going to ask for degrees. Okay, so sine of 20, what do we know about the amplitude of sine? Great. Okay, so Natalie just came out with what I was thinking of. So 15 over 4 is out of the range for sine. The range for sine is what? 1. 1 is the amplitude, and it ranges from -1 to 1. So we know that sine of 20 has to be less than or equal to 1, whereas 15 over 4 we know is greater than 1. Okay, so because of that, the limit as x approaches 5 from the left, which is 3x over x minus 1, does not equal the limit as x approaches 5 from the right of sine of 4x. Okay, because of this, it is not continuous. Okay, so I'll let you write that down for a second. Hopefully you can read my handwriting. I promise I will get better over time. I'm gonna scroll back up in a minute. But what I'm gonna do is look at the options that we have. And one thing I really wanna pay attention to is if that 5 didn't work, what do we know about the point 4 to 6? The interval, not the point. The interval from 4 to 6. Is that continuous? No. Okay, great. So we've ruled out every option except option A. Now, I'm saying that we ruled it out, but that also means we've proved that everything else can't work, and that we've proved option A can. When we plugged in when we plugged in 0 and we found that the function f of x is continuous at 0, and -2 from one side we can say is continuous all the way to 1. Now I had that as 2 before. If I had kept that as 2, what would have been wrong with A? Why wouldn't A have been able to be correct if I said that the interval went all the way to 2? Take a look at the second piece of your function that it would have been in. Look at 3x over x minus 1. Good. Okay, Corey got it. So because it's discontinuous at 1, we can't have 1 included in our domain. So yes, our interval can go up to 1, but it cannot include 1. So A, -2 to 1, is our correct answer here. Yes, good job, Corey. Do you guys have any questions on that problem? Feeling good about it? Okay, so let's do one more problem for the night. Let's look at, we're good on intervals. Let's look at this problem here. Okay. So this is another piecewise problem. Get ready. So, oh, why can't I draw? 1 second. Here we go. Okay. Let f of x be, let's look at this. F of x is x squared plus 1. This only has 2 pieces. For x is less than or equal to 2, x less than or equal to 2. And then we've also got 4x plus k. So let me rewrite this plus 1 because that is going to get confusing. 4x squared plus 1, 4x plus k for x is greater than 2. Okay, and our job is to say if f is continuous at x equals 2, what is the value of k? Okay, and our options are, another multiple choice, A, 1, B, 3, C, -1, and D, 4. Okay, I'm going to give you guys, okay, I see some people missed something. That's okay. This is going to be posted on the website, so don't worry. A new problem right now, this is another one like you'll see on AP. This is one you will probably definitely see. So feel free to look this up, but this is a great problem to have to see tonight too. So I'm going to give you guys about 30 seconds to try and start this on your own, and then I'll keep talking so that I'm not just sitting staring at a screen of myself. So take a minute to start doing that, and then I will start doing it out. Okay. Okay, so this says continuous. Okay, so again, going back to continuous and what we've been talking about this whole time, what do we have to check to make sure is true? What's our first thing we have to make sure? If it exists. Yes, if f of 2 exists. Okay, what is f of 2? Did you guys find that? F of 2 is 5. Good. So actually, let me write out the steps so you can see it later. So f of 2 is going to be 2 squared plus 1, which is 5. The one that is less than or equal to 2, because the other one is not equal to 2. Okay, now the next thing we have to say, or we have to figure out, is about our limit, right? So we have to know that the limit as x approaches 2 from the left equals the limit as x approaches 2 from the right. Okay, so one of these we know. The limit as x approaches 2 from the left is going to be from our x squared plus 1 function. Okay, so we plug in 2 squared plus 1. Again, we get 5. Off to a good start. What has to be true about our limit from the right in order to make this continuous? Okay, great. So the limit from the right has to be equal to 5. Has to be, not the letter B. Okay, so if the limit from the right has to be equal to 5, we know that 4x plus k has to, sorry, not plus 5, plus k has to be equal to 5. Okay. Do we know what x is? 2. Great. 4 times 2 plus k equals 5. So we get 8 plus k equals 5 minus 8. K has to be -3. Wait, -3? Yeah, okay, my bad. One of our options should have had a negative sign in front of it. Yes, Davina, you're right. Option B should have been -3. Okay, awesome. So K has to be -3. So if this were a free response question, AP would want to see something like f of x is continuous at x equals 2 when k equals -3. And they would want to see all of the steps that we just did out before that. So they'd want to see that we know to find something is continuous, we have to show that the limits are equal. We have to show that f of that point exists. All right. So we're just about out of time, so I'm going to stop there. Let me get you back to my PowerPoint so we can wrap up this session. Great job tonight. All right, let's go back. Okay, so we just did some practice problems. And now let's summarize. So continuity and how to find it. So we want to check the domain of our function. If it's a polynomial, we've got all real numbers. We don't have to worry about continuity. If it's anything, if there's any spot in the domain that is not continuous, that is a piece of the function that if you're within that interval, in any point within that interval, you will not have continuity. But if you're within that domain, you will have continuity. With a piecewise function, we really just have to check every point where the pieces swap, where they split up. We have to check all of those pieces because they might not line up, and they might line up. Sometimes they can. Okay, so if a function has a domain of all real numbers, so that's a polynomial function, it is continuous on any interval, and otherwise we just check to see if there are any domain problems on the interval or if it's piecewise. Okay, great job tonight. So lastly, what we're going to do next in our next session at the end of this week on Thursday is we're going to talk about types of discontinuity. So tonight I've been talking about how things are not continuous. There are specific ways that they can be not continuous, and that's our type of discontinuity. Sometimes the discontinuity is irremovable and there's nothing we can do about it. Other times we can find things to replace it and make our function continuous. So if you want to see the next part of this lesson, tune in on Thursday, the 19th, which is this Thursday in a few days at 8 p.m. to see Mr. Kosoff. He will be teaching that. And again, if you want more updates on when you can see these, please follow us at any of these links. Thank you guys. You've been awesome. Thank you all for participating. I'm glad you had a good lesson. Let me know if you have any feedback. All right. Have a great night.